Welcome back to Neural Networks for Architects. This is the second day on the mathematical thinking towards neural networks. And this chapter 10 is on the law of large numbers. In the last chapter we introduced and discussed the exponential growth or combinatoric explosion, which is a very principal problem of all systems and structures and functions, and we call that it's a problem of gravitational people, problem of reality and the limits of our world, our real world, in a talk with Wittgenstein. So we also said that the aliens, the people of light, they don't have this problem. So they're sitting at the edge of the world and they are looking, they picture the world from different perspectives. They think algebraically and with symbols. They don't signify things in reality, they symbolize things. They juggle around with these irrational symbols, and then they talk. And we've seen that this exponential as well as the logarithm is bridging their world or their domain with the real domain. So their picturing is in mathematics corresponds to the logarithm, and their voice is corresponds to the exponential. So it's the alien's voice and what we have with the combinatoric explosion. And it's the voice and it sounds. And to learn from this alien's voice, this is what this chapter is about. So the combinatoric explosion or the exponential growth always gets, it's a misunderstanding if you put that real, because it's a bridge to communicate with the aliens or with the ratio. So this is what the law of large numbers is about. It's with mathematics and it shows you, I think, the most simple way how to deal with this, because mathematics is not about numbers or formulas or proofs. It's a way, it's an uncorrupted way of thinking, and I think with mathematics you can get how this alienation works. So therefore let's focus on these examples. So this is what I think. This is the origin of the exponential. It never was in the numerator. It always was in the denominator, like here. And then it says it's not about exploding, as it had been with Malthus and in all these catastrophes. It always had been in the denominator, and with that it simply says it's complicated to start to learn a new language, a programming language, or Chinese and so on. It's very frustrating and complicated at the beginning. Then you get proper results, and if you go to perfection, it takes an infinite time. You can't we said you can't grasp a reality. So that's the logistic function or learning curve. So how we get there? This is with Bernoulli. Imagine you have a die and you throw it 3 times. Then you have this series here. So it's always different. You get another series. So then, thinking that as a system as we discussed, so they are connected as a line of throws. So very simple connection, and we simply say it's a system of 3 or here 12 throws. So if we think of that as a system of throws, then we can, for example, accumulate and then make the mean value, accumulated mean value of the throws. And then you see what happens. If you do it again here, the mean value goes somewhere and somehow goes towards a certain number between 3 and 4. So it starts very exotic and extreme values and ends here. So and here, for example, you see that if you do it 1,000 times, it goes in very specific or individual ways, but it always converges to a certain number, in this case 3.5. So, and this 3.5 is the alien's voice. So that's the ideal we are talking of. So this is the sound of the machines you can't see. So these blue ones, these are of reality. This corresponds to the product, and the red one is the production, the sound, the voice of the aliens. So, and if you put that and look at a long system, then it converges to that, but it never reaches it. So this is how the law of large number, Bernoulli 1713, 300 years ago, set it up. Yeah? Therefore, all systems, all productions, all structures, all functions are ideals. And the environment, so they're excluding things from outside, as we said, and the environment, it's very important, is not a system. Keep that in mind if you are environmental agitations and discussions. You can't make it systematic because you can't grasp it. It's there. Every system, whatever you gravitationally think or do, is embedded in the environment and can't grasp the environment itself. But aliens can talk about it. So, then there are nonsense systems, and we can distinguish, we can try, there's a very interesting a turn, how you can detect sense within the voice of the aliens as gravitational people. And this is what we did all 18th, 19th century, and there was nothing else. So the first is nonsense. So this is again with the dice. So we look at a set of a system with parts, and there's no connectivity in that. For that, we don't have to look at the dices and at the sequence of throws, but you have to so we have to look at the faces and ask whether there's a connection between the 1, the 2, and the different faces. And of course, we know with the die, it's about not having any connection. It should be completely random. So then we are looking at a system of faces which should make no sense. It's nonsense. It's random. So it's a production which makes no sense. So having that as a function, it's here. So we throw it 100 times. So this was it done. Then we count it. And then we get the frequencies and the percentages of it. And you see this is a certain line. And it's working like this. If you do that 100,000 times, then you see the frequency of each phase again converges to a certain number. So it's like this red line we had with the law of large numbers, but now we are with the connectivity of things, and it converges to this line. This should be red, because it's an ideal, and because they are of equal distribution, they make no sense. There's no distinction in these numbers coming out. So they're all the same. So we see that as white noise. So we have a kind of dice throwing machine, a random integer for so we just do these points, and then we have white noise, and always we're doing it as another white noise, but completely without any sense. More attractive is this Brownian motion. So we simply do these real numbers. These are steps of an animal, and we say an x and y, and we accumulate. So we always make a next step. We accumulate that, and then we make a Bézier curve for that, and then we see this is random walks, always different. This makes no sense. So, having that as a background, what happens if we make a system? And how to detect whatever is there? So now let's go here. What we do now is we take random dice and throws, but we cluster them into three, in groups of three. So, and then we simply make an addition. So we make the sum of all these of this sequence of random numbers. We make them as a system, and we do that always the same. So there's a regularity in that because we do this addition. So which means this is random. We add a system, a certain structure to this random, and we get these throws, these numbers here. So, and they are not random at all any longer, because they are additions. So they are random numbers, but we put them into a certain systemicity, addition. So if we count this, we can do this here. Oops, what do we have here? So go here, go, no. Come on, kill it. So if we count this, then we get this bell curve, and we call that normal distribution. So, and this always says this is an indicator that in a population of events there is systemicity. So that's it. So we can somehow go in sync, we can tune towards the voice of the aliens. So now this is what we can imply. So we take, no, it's too much, read it. The prediction of events. If we have that, this ideal, now the idea is how to produce events of this kind. Make a function of that. And this again is a little complicated, with like we had with these power series, similar things. And you see, for example, what we know is we have the mean value. So we know these events have a certain mean value. So, and then we say how wide is this, how specific is this bell curve. This is the standard deviation. You simply do this like this. And here we are. So, and this now creates a function, makes an ideal out of that. So it's like like with this law of large numbers, getting from these examples we had with throwing the die, and the red line, the ideal. So this is how to make an ideal for the numbers we had. It's always a little different and absolutely crazy. And you see this, it's an exponential, and it's irrational, and here you have a symbolic representation of that, like the aliens do. This is a function, and now we can produce this red ideal line of the characteristics of a system, which is this curve. So any system, all species, and you're with, it's a central limit theorem by Moivre. And this produces now not white noise, but this kind of distribution. And you see, so now it's not random any longer, so it has a certain systemicity, and our function is able to work like in sync with the aliens' talk, in harmony with them. So that's the central limit theorem we have here. So that's how try to learn what they talk. So, and this is what we call statistics and stochastics. So, stochastics is what we did here with Moivre to predict the next event. It's a clear distinction between statistics and stochastics. Stochastics predicts the next event. Statistics counts the events observed. So therefore, statistics learns from the past events. So that's the very idea of the Euler and the learning curve. And statistics is positively cashing out. Forward in time with stochastics, statistics is backward in time. So, and this is very interesting. You have these French guys doing stochastics prior to the statistics. It's a later conception, which is with Baynes. So if we go then here, for example, that's interesting. So in architecture, it's if you have Beaux-Arts, this mimics the growth of things. So this is Jugendstil and Beaux-Arts, for example. You see, it's the growing itself. Try to getting better. So this is how you kind of domesticate the growth of things and mimicking that. Whereas this here is arts and craft, and this is mapping the growth. So these things are already grown. It's a fine difference, but I think that's very interesting, very important to get. That you have, if it's all about prediction in gravitational thinking of 18th, 19th century, then you have these huge traditions, the French and the British ones. The one is looking like this, in this direction, the other in time, because gravitation is all about time. And therefore, for example, in science you have the statistical way with the evolution, like Darwin, the reference is here. And if you go with stochastics, my most liked example is how modern medicine evolved with the epidemiology. And this turn, like I had it here, this turn I'm telling here is most interestingly developed with Foucault, and very detailed, the birth of the clinic. That you have, for example, with the if there's an epidemic like Corona today, they learned how it will be in 5 and 10 days, and they learned and they predicted things because of measurements, of populations of measurements. They tried to hear the alien's voice, and then they, like us with the vaccination, they started to vaccinate people with the viruses to make them sick and make people healthy, artificially sick to prevent the spreading of the epidemic. This needs this kind of thinking in the 18th, 19th century. This is all analytical, classical science, analytics, and so on. All historicism is about this. So, I think that's it with the learning and what statistic is different from stochastic. Very complicated to get, and especially in the English-speaking countries or discussions, simply not present as a problem at all. So be very careful with that, because we have to make our points exactly at this line. Thanks for watching. See you in the next tutorial.